I had to take my jacket off. It's just been too hot for me today, so we'll go this route. We're going to talk about electrical today, and we're going to talk. There's a lot more than one class worth of stuff to talk about electrical. The guys that TJ and Jaredon teach a 4-year class on electrical for the journeyman electricians. So there's a lot to learn from a knowledge base, and all of it. There's not a day that goes by that they can't or don't or shouldn't talk about electrical safety, because electrical safety is rather permanent if we get it messed up. It does enormous amounts of human damage, and we don't really understand all of it, but we understand enough to know at least what is hazardous. We don't always know the physics of why it is hazardous. In other words, we don't know if lightning strikes us, which way it strikes us, from the ground up or from the sky down. There's argument over that amongst the physicists, but it doesn't matter if it's me that got hit by lightning. Either way, it's going to be a life event and maybe a life-ending event. So we're not supposed to play golf when it's lightninging, right? And they make you get out of the pool and all of that stuff, which it's all something that we grow up understanding and knowing, but it's surprising how many bosses don't call it when there's a threat of lightning and they've got a crew outside working, worse yes, on a roof or on a structure, steel framing, and so if you are in a work company that potentially has crews outdoors where there could be a threat of lightning, this is a very viable issue to discuss long before the weatherman forecasts a storm. It's something to talk about in your job hazard analysis. It says, we from time to time have people that are working outside the building. Now that may be out on a job site, it may be on your loading dock, where you're exposed outside to where you could get struck by lightning if it was a lightning kind of a day. We replace our lightning arresters on this building. No, I don't know about this building. Building A and Building B I know about. Building A and Building B, the lightning rods are about every 10 or 15 yards apart, all the way around the perimeter of the building. They're about this long, and they get hit once and turn black. We have to replace them. So there's a visual that it's been struck by lightning. So we are constantly replacing lightning rods on these two buildings here. You know, constantly. I mean, every few weeks there are lightning rods that have been hit, almost year round. In the time of year, right? I mean, right now it's big time, but in time we have time of years that we don't think we have storms here in St. George, but we do, and it's not an unusual event. I don't know what the number is. I can ask Tom. He does most of it, and they order the replacement lightning rods. They have them. We have them in stock, and so it would be foolish to think that your dock at Wilson Electronics isn't exposed to lightning. It may be that it doesn't very often get hit. These buildings are on an old airport. I don't know what the material is made underneath, but it may be a magnet for lightning. And we're on a mesa or ridge. We're up high, so it's a likely target here. So it's probably that down in the valley of St. George, in the bowl, that lightning hits far less. But Foremaster Ridge is on a ridge also, and we have other hills and places where houses are. And the guys that maintain the cell phone towers report the same thing. Cell phone towers get hit often by electricity, and that's not a problem if they're properly protected. It's a problem if you're working on one. And so you have to have a policy. You have to have a procedure. You have to have a technique that is the rule that allows the worker not to guess whether or not they ought to be there or not. The company needs to make the decision of how do we determine at what point in time we ought to call work and stay in shelter where we're not exposed to lightning. Every job site's different, and the meteorological people can be talked to, the university as physics people. There's resources we can get in terms of establishing safety mechanisms, and OSHA will help us actually with that too, because they don't want you hit with lightning. And when lightning hits something near you, it can jump to you, right? I recall my brother and I, when we were kids, watching a lightning storm from the garage. The garage door open, we're safe in the garage. And there's a maple tree out on the driveway that's, 20 feet, 30 feet from a big, mature maple tree that got struck. Lightning went all the way down and then came straight at us. And it hit the post of the garage door. Didn't hit us, but that's permanently tattooed in my retina. Standing there watching, when there was no point that you couldn't even blink. It happened so fast. It was just. But there it was coming. Gary, my brother, did you see? Was that coming at us? That was coming at us. It was. And so, people have been struck by lightning in their living room through open windows. So there's their number was up. It's like you did something bad. So next time, you might not want to do that. So OSHA has put together a lot of training materials for us to draw from. We're going to start with a packet of PowerPoints that I didn't produce, that OSHA supplied to me as a trainer. This is for the 10-hour outreach general industry, and it's a starter. It's just to kind of expose us for the first time to electrical safety if we haven't been firsthand doing electrical stuff. And most of us aren't employed in the field of electrical stuff, high power electrical anyway. We may work with electronics, but how often at Wilson is the stuff you're working on actually powered? Most of the time it's power off, right? You're building them from scratch. And so we have stuff around us that has power, but there's a lot of interesting things to understand. Like I say, we generally think lightning comes from the sky. It may be, we generally have thought it was DC, positive to negative, then Earth was ground, because we kind of think of Earth as being ground. We call it the ground, as a matter of fact, right? But currently, theoretically, we don't know if it's direct current or alternating current. There's evidence that says it actually goes in both directions, and it may initiate from here as often as it initiates from there. That's all really hypothesis at this point. Nobody really has factual data. There are some things in this earth that are in this world that we take as fact that really we don't have an understanding. We know it's a fact, but we don't have an understanding of how it works. And gravity is an example of that. We know gravity's there, but we don't really know how to where it comes from. It's an it's an enormous amount of energy, but we do know that if we trip and fall, we're afraid of heights because we believe in gravity, but we don't understand gravity. We don't know, and there's even a gravitational pull of the building we jump off of that pulls you to the building. Theoretically, that part is provable, but we don't really have a good understanding of the physics we can't reproduce gravity very well. In fact, it's difficult for us to create anti-gravity chambers where we take current physics and try to defy gravity. We think the aliens have got it figured out, but we don't know that for sure either. Electromagnetic energy is another thing. We know it exists. We see that. And in our era of awareness, the understanding of electricity was still foggy when Benjamin Franklin was alive, which wasn't that very long ago in the scope of the earth. And Ben Franklin is known for putting his kite up in the air and putting a key on the end of it, right? And trying to bottle electricity, try to capture it, and I think every kid since then has tried to do that as well. And Tesla had some theories that may be right, and the conspiracy people think that the U.S. government has sealed his lab notebooks. Anyway, they're not available for us to read, and I would love to, because I think one of the most fascinating projects that I think that I hear little bits and pieces about and read with Tesla, Nikola Tesla, was he believed that we could create a capacitor in a hill or a mountain. And when lightning struck it, it would charge the capacitor, and that if we configured it properly, it could hold that energy until we needed it or wanted it, and we could discharge it.
Fast amount of energy.
Enormous amount of energy. And when you look at a capacitor is two conductors separated by a dielectric and rolled up in the case of a can capacitor, this way or this way, doesn't matter. That's basically what a capacitor is. And we can create a capacitor with an extension cord if it's 200 feet long. That cord becomes a capacitor and holds a charge. And it's just it's your extension cord. But it's two parallel wires separated by a dielectric. So what if we had two parallel conductors, like a vein of iron ore, separated by dirt, and another vein of iron ore, and lightning strikes that? Would it hold electricity? Tesla thought so, and he experimented with some stuff that's a big secret now. None of us know what it was. I don't know why we don't know, except it wasn't our time to know. And I'm saying all of this just because electricity is fascinating to me for these reasons. We use its power in motors. We use it, we're talking about electric cars. We're using electricity as a source that's changed the world since we've harnessed it, which has only been 100 years or 150 years, something like that. And so we understand this much about it, and we can make it work for us a little bit, but there's a lot more to be discovered, I'm sure, and we don't yet really have an understanding of when I touch something and it shocks me, what happened? How did that charge actually create a shock? What does it do to my body? And it cooks, it flows. And so we know some things about conductors. Electricity goes through conductors. OSHA doesn't want us to touch conductors when they are electrical charged. And I don't either, because that's how you get zapped, right? But in the human body, what is it that conducts electricity?
Everything?
With enough power, everything will conduct electricity for sure. We talked about that. Our skin normally, a cowhide is a cowhide. We put cowhide gloves on, and it kind of protects us from shock, right? Cowhide gloves, if they are dry, don't conduct a lot of electricity until there's a lot of power. And then at some power point, like leather gloves don't protect you, right? You need more better insulated gloves that are rated for protection. But a cowhide is not all that different from human skin. I mean, skin's alive, part of it, and the moisture in the skin will conduct electricity, right? So if we are sweaty, the surface of our skin will conduct a lot of electricity because the sweat is saline solution, right? It's salt and very good conductor of electricity. How about your blood? Blood's a great conductor of electricity, a great one, which means I get zapped here. The wiring is the skin that's wet on the outside and my capillaries and veins and arteries, right, that are wired right up to my heart, right? So I get zapped, and that electricity has an option in some cases to follow my blood. And when it does, we have a high possibility of dying, right? And the other thing that's interesting about the human body is that we're electrical. Our nerves are the synapses in a nerve that sends a message is an electrical pulse inside the human body. We're made that way, right? Our brain stores information and data in electrical pulses. And those connections of the in our brain that can be rewired, the neuroplasticity that allows our brain to, if we get damaged in one spot, to rewire our head, and some very crazy experiments have been done. One of my favorites was done 50 years ago. At this point, a university gave a bunch of college students a pair of glasses that flipped everything upside down. And they had to wear those glasses all the time. And after about 30 days, most of their brains flipped the image back over. And now when they took the glasses off, everything was upside down. And nothing had been surgically done, no medicine taken, just normal human beings where our brain is processing information over and over and over again and figuring out, this is upside down. I got to compensate for it. I got to fix it. I got to do something for it. And our brain does. It rewires. And so these electrical connections that are going in, for my muscle to fire, there's electricity that goes down and tells it to move. So we have a wiring structure in our nerves also. So we conduct the water on our skin. The body is 95% water, by the way. So that's how magnetic resonance imaging happens, right? Is that when you think about we've all heard about an MRI. We've mostly had an MRI done. But an MRI, the way it works is we capitalize on that 95% of the human body that's made of water. And a water molecule is what? H2O. So there's an O molecule in the middle and two hydrogen molecules on the outer shell, the outer valence of this molecule. Electrons are negatively charged. So when I expose that molecule of water to an electric field, it will orient itself like a compass needle does that points to magnetic north. So if I create a magnetic resonance imaging, MRI, I create a magnet around your body that lines up all the water molecules, take a picture. Then we move the magnet, take another picture, move the magnet, take another picture. We see what didn't move. What didn't move is not water. Now we look at that and negatively create the image of what didn't move, and now we know what's inside. I mean, that's kind of a simple way it works, but that's how it works. And that's amazing, isn't it? The electricity does really good stuff, but somehow it can also catch up and kill us. And what does it do? It can be if we get zapped with most electrical currents that are AC, it's at a 60 hertz frequency. And your heart is not operating at 60 hertz. It does operate at frequency. It's lower than that. And at 60 hertz, your muscle doesn't know which command to listen to. Your hypothalamus, it says beat for your heart to beat, or the electricity, it's saying beat faster. And so your heart defibrillates, right? And as your heart defibrillates, the pump stops working. And when the pump stops working, your blood stops flowing. When your blood stops flowing, your brain has no oxygen. And you die. And all that happened was you just got enough frequency that it stopped your heart, which can happen sitting in the back seat of your buddy's car with those giant subwoofers. If they run the right frequency in those subwoofers, it can stop your heart.
Really?
Yeah, really.
Never heard
Yeah,
that.
you got to screw with it. It's a very low frequency. I had a CD that allowed you to do that one time to try to check it out, and you could feel when your heart was getting ready to stop, when it was just about in sync with the.
Well, you wouldn't want to.
You didn't want it to stop, but you were ready to fibrillate if you needed to.
Just right in front of the hospital train.
Almost there. Just a little more gas. No, it was actually recoverable, they thought. And I felt it, so it's real. I know what, but our bodies are amazing bodies, right? And electricity is, although greatly unknown, it's greatly respected. It does incredible stuff for our lives. But at the same time, in our workplaces, we have a job to be safe. Does electricity go through a stranded wire differently than it goes through a solid core wire?
Yes.
How so?
Was that a guess?
She was a 50-50 guess. It was no, she knows because she works with wires all the time.
Wire, right?
Yeah. So most of electricity, the electrons flow on the surface of the copper or the conductor on that. So if you've got stranded wire, you've got a lot more surface area, and so theoretically, it can hold more. It can flow more current. However, it also gives off heat as it does that, and so those melt faster than solid core does. So it's a trade-off. How much power you're pumping through? You're working with 14,000 volts at Dixie Power. You're going to want a a wire that can handle that, right? And these guys won't. These will melt down. And every high school kid, their first stereo they installed in the car, they used wires like that. And if they were lucky, they didn't burn the car up, right? Because those catch on fire, right? Because they've got too much power in their amp that they're putting through the wire. And so you wire your subs with 1/0 or 2/0 wire. It's this big around, welding wire basically, right? So it can be a conduit for that much power. So the wire selection, the ionis, it's pretty neat when you smell the air after lightning strikes, after a storm. If you notice that when you go out, the air has a sweet kind of a fresh smell to it often. Pay attention next time you're around one and lightning has been striking close by. Go outside, that's ozone. So the actual hydrogen's been burned out of some of the air, and we have a sweeter, a mutated molecule, if you want to call it, still floating around in the air. And ozone, you can buy it at the store. It's not, specifically dangerous stuff, but it's cool. And the hotels use ozone just for what it's worth. If somebody breaks the rules and smokes a cigar in a hotel room, they bring this box in here and they run that box for a day and they charge you an extra $100, and that box produces ozone, and that ozone will
theoretically it kills mold and everything.
Yeah, it takes a lot of smell out of the air and stuff like that. The smoke
detectors.
Not the detectors, but the casinos have these boxes in the air that kill the smoke. Those are ozone plates. Those are plates of high voltage electricity that produce ozone in there. So the air goes through and it grabs the smell molecule and it sticks to that and it fills up a filter full of the air, the particles that were causing the smell. That was a goat trail. I'm sorry, I don't know where that came from. Because we're looking at wire size. That's what it was. So OSHA wants us to understand what are the major electrical hazards that we deal with. What types are they? What kind of choices do we have to protect ourselves? And where are there requirements in place where we have to, as an employer, protect workers from electricity, other than the fact we want to protect everybody? Electricity is kind of defined as the movement of free electrons between atoms, and there's quite a lot of science behind that simple statement, and we touched on a little bit of it. Current is the movement of electrons. It's like the flow of water. So when we talk about electrical current, we're talking about in an analogy of the water in a stream at the Virgin River, the amount of flow of the river in the Water Conservancy District here. They measure 24 hours a day, 7 days a week, the flow of the Virgin River, because we want to know what is the availability of water in our. It's one of the heartbeats that keeps us alive, right? We need water, and so we measure water in flow, and water is a flow of what? It's a flow of molecules of water, H2O, and they measure it in terms of gallons per hour in the river. So how many gallons per hour go past a certain point is the flow of the river. In electricity, the flow in a wire is exactly the same thing. They measure electrons instead of molecules of water. They're measuring negatively charged electrons, and they're measuring how many electrons per second go by a certain point. And there is a definition of how many it is for one. The measurement is amps for current. The measurement for water flow is gallons per hour. The measurement for electricity for electrons per second is amps. How many amps of pressure do we have? How many amps, not of pressure, how many amps of flow do we have? And so that is one term in electricity. Another term in electricity that we have to deal with is the idea of voltage. And voltage is the pressure. It's often referred to as the voltage potential, which means how much difference between these 2 points. 50 volts, that's the amount of potential of pressure of the voltage. So in the Virgin River, it's not what is the flow, but how forceful is that flow. If we looked at a garden hose instead of the river, where the hose is contained, if you constrict it a little bit, the flow changes because you've got a restriction, but the pressure goes up, right? We drink out of the hose that way because it's when you pick up the hose, it's just going like this, and you want it to have higher pressure. How do you raise the pressure? You squeeze the hose so it's constricted a little bit. Now it shoots out enough you can drink out of it, right? We've all drank out of a hose that way, or we've watched somebody else drink out of a hose that way. We didn't know it was bad to do, just it was what you did if you're thirsty. So we have the current is the flow of electrons. We have voltage is the pressure that those electrons are under. So we need a certain amount of flow of water to water the grass at your house, but the sprinkler system won't work unless you have enough pressure. So the water pressure, you'll get a gauge at Home Depot if you want, and you can hook it up to your water, and it will tell you got 14 pounds pressure or 50 pounds pressure. One of them's going to blow your sprinkler heads off. The other is not going to be enough to get your grass. Right? So you got to get the right amount of pressure in your water system in order for the flow to be adequate to what you want. So it's a combination of a number of water molecules and the pressure that they're under that makes our grass work. And makes the water in your house work, all of those things. And in electricity, it's the same thing. There's a relationship between flow and pressure. And that is, it's not pressure that kills you. It's flow that kills you. If it were pressure that killed you, a taser at 150,000 volts or higher would kill you. Right? And it's only occasionally that a taser kills you. I mean, it's designed not to kill you, right? It's designed for your body to be able to stand that because it's not over a long period of time. It's a bzzzt, and your muscles freeze up or constrict or whatever, and you hit the ground. But you didn't get killed because it's not the voltage that kills you. It's the current that kills you, and it's a very low current that zaps you in a police officer's taser. And they're rated for different voltage. You could buy tasers from Alibaba that you and I can own that are at, I've got a flashlight that's got 50,000 volts. It's like a hot cattle prod or something like that. And that's not illegal to own in the state of Utah, and it's maybe illegal to use wrongly. I think you got to. It could be dangerous to somebody there. Then resistance is how hard is it for those electrons to flow through that material. And if we look at the periodic table of elements, we see that they're organized. I mean, you may picture one in your head. I maybe later we'll put one up that we could look at more specifically. But conductors and insulators are kind of in groups in the periodic table of elements. And towards the right side of the table, all the way at the right side, the final column on the table of elements, periodic table of elements, is a group of elements that's called the noble gases. And the noble gases don't conduct electricity. They are inert. Helium, neon, things like that, argon, that are non-conductors theoretically. And on the other side, you've got metals that are good conductors. Copper, aluminum. We got a group of metals on the periodic table that are friendly to conducting electricity. And then we have a group that's almost sort of in the right center, kind of a group here, of something that we call something different. Anybody know what that group is called? Semiconductors. Now, Wilson Electronics, you use semiconductors. Without semiconductors, you're out of business. Everything that goes on inside an amplifier is based on semiconductors. Our world is controlled with semiconductors these days. And when semiconductors are analyzed at the molecular level, what it says is that material, silicon, let's get that right. Silicon, germanium, those are in that clustered area, and those materials sometimes conduct electricity, and sometimes they don't. And in a transistor, we control whether it does conduct or does not conduct by putting an electrical charge. We have an emitter, a base, and a collector. Those are the three components in a transistor, and by controlling whether there's voltage at the base, it determines whether or not a current will flow or they will conduct between the emitter and the collector. And that's an amazing discovery. It was discovered, the guy that discovered it actually, John Bardeen, was my physics instructor at the University of Illinois. And he won the Nobel Prize for inventing the concept of a transistor. And there was another scientist that was neck and neck with him, and collectively they advanced some more transistor technology that we're all familiar with. But that happened in the 1950s. That wasn't that long ago. And that we figured that out. In fact, kind of a funny story, on campus one time, he later went on, by the way, to win a Nobel Prize in something else. One of the only people in the world that's ever won 2 Nobel Prizes in 2 different topics, which is unbelievable. The dude's smart. But anyway, besides that, they were having, I don't remember, but a national organization was honoring him for the transistor, and they were having a big assembly and presentation, and he was late for it because his garage door transmitter didn't open his garage door. The transistor burned out on his garage door opener, and he had to go to plan B to get it, and he was a few minutes late for the ceremony, which I thought was absolutely a hilarious story. So electricity, we have current, voltage, and resistance. We also have that issue called insulation. And insulation is what OSHA wants us to understand. When does it protect us and when is it inadequate? So we will go into that a little bit. We've talked about conductors. Insulators are things that normally have a high resistance to normal amounts of electricity. And we've got a whole bunch of those things. We buy shoes that have insulated soles such that we have better protection against electricity. Electricians often wear boots that have that treatment on the sole of the boot so that their protective clothing isn't as likely to conduct electricity. The hard hats that they would wear, different types of things that protect them. Now you guys know about grounding more than probably any group that I've talked to here, because you deal with something called ESD all day, every day in your manufacturing facility at Wilson. That's electrostatic discharge is what that stands for. But what that means is the flow of electricity. And if the flow of electricity sheds off my body because I brushed my hair and I created a static charge and I touch a circuit board and before I put it in an amplifier, I most likely have zapped that circuit board, right? You get training on how that works, and you ground. We get a ground clip that goes, the floor in your facility is treated with a conductive material that bleeds off ground, right? So that the floor at Wilson Electronics looks normal. It's not normal. I remember when they coated it. And I don't know how often you have to redo that, or I don't know how it works, but the floor itself is a conductor to help ground the electrostatic discharge that normally builds up in a facility. So that is a safety for the product, but we can get enough electrostatic charge because it can do human damage too. Electrostatic discharge is not a trivial type of a thing. When electricity goes in us, it also comes out of us. And often, just like gunshot, the exit wound is often worse than the entry wound. where the electricity goes in, it comes out the bottom of the foot, your hand touching over here, your other hand it's coming out of, it may blow out that other hand worse than the one where the electricity came in at. We don't understand it very well, how that works or whether the injury is going to be worse, but what we do know is that when we have the flow of electricity, if it gets rerouted and it goes through us, it's going to cause a problem, and that's not news to any of us. OSHA says be safe. We can get hurt from burns, electrocution. By the way, what's the difference between being shocked and electrocuted?
Is shock just quick and electrocution like snap more?
You're on the right line, but the difference, if you live, you weren't electrocuted. It's if you live or die. If you die, you were not shocked, you were electrocuted. If you live, you were shocked. And not that it makes that much difference, I don't think, of what term you call it. I just want to live. So electrocution and shock are the same thing, depending on whether you survive it or not. Arc flash. We're going to watch a video on arc blast and arc flash because I think it's one of the things we need to manage, and we need to have some understanding about fire and explosions are other factors we're going to look at. When we get electrocuted before we die, we catch on fire. Usually we have electrical burns that are serious and sometimes fatal. If we're electrocuted, it's fatal by definition. But
Always die?
I'm sorry?
Do you always die if you get electrocuted?
Yes, if you get electrocuted, you always die. If you get shocked, you lived. That's just a technical term difference. Both are exposure to electricity, and the ones you die from could be less electricity than the ones you survive. It's not how much electricity it is. It's where it goes, where the path goes, and does it get to one of your vital systems where it makes mush out of it and kills you from that. So there's a physiological death that occurs of what it does. I mean, if it's a fire, if it burns, you burn your liver, you cook it, and you don't live. Your liver shuts down and fails, and you die. And that's true of most of your organs if we cook them, which sometimes there's a lot of electrically related damage. I talked about cell tower workers. Cell tower workers have been in history exposed to the microwave energy that's coming off the cell tower when it's in transmit mode, and that's the same as standing inside a microwave oven, and that's considered an electrical exposure, but it's a microwave energy exposure is what it is, and it can kill you. And so the teams that install and service cell phone towers are highly trained, and they have a lockout tagout just like you would expect, and we've learned that the hard way, because what didn't look like an exposure, you can't see it. You don't, and you may not know it when it happens. It may actually cook you without you realizing it. And shielding is pretty normal on microwave. Our cell phones are microwave energy operated, and your microwave at home is, of course, and there's an interesting thing when you look at the inside of your microwave door. It's got glass in it, right? So you can see what's going on inside the microwave, if it's sparks producing or whatever is happening there, so you can see it. But when you look closely at that glass, it's got a screen, right? And that screen's full of holes, right? And those holes are similar to the holes in the advertising poster at the Maverick door. You can read the message on the poster, but you can also see through the holes, right? And you can see what's going on outside, and it's pretty odd the way those holes work. So through those holes you can see what's going on inside the microwave, but guess what size the holes are?
Okay.
The holes are smaller than 1/4 the wavelength of the microwave energy that's being used, which is usually 923 megahertz, I think, something close to that. But anyway, the waves that are cooking your food inside are too big to sneak out the hole. And so they were forced to put those there. Why? because every little kid puts something in a microwave and pastes their nose to the glass to see what's happened to what they cook. And in the early days, they cooked their eyes. Because we didn't know about microwave yet at that point, right? The first microwave oven was produced by Amana, and they cooked people and parts of people accidentally. You know, we reacted quickly and understood what it was and created, proper shielding. And so with proper shielding, OSHA says you're safe. You can look in your microwave. But if you damage the size of the holes on the microwave screen, don't take that microwave to the DI, cut the cord and throw it away. Because now microwave energy can sneak out of that. And when it sneaks out of that, it can cook something outside of the microwave, including, your cat or whatever. So you don't want to do that. And OSHA says, not that you must take that out of service.
Real quick, Steve.
Yeah.
125 volt, which is in all our houses and all the sockets, is relatively safe, right? Are there circumstances under which you could get pretty serious damage from it?
Yes. It depends on where it goes. I'll show you, if I don't have it handy, I will show you a chart of how many milliamps it takes to stop your heart. But it has to get to your heart, which could be a freak. It could be normal shocking from an electrical outlet is really through my hand, not through my heart. It's right in, right out. And so you completed the circuit with part of your body, and it hurt, or whatever. But it's probably not going to get to where it's going to kill you. But you don't treat it that way. You treat it that it will. And because it can. And it does not take very much to actually kill you if it gets to the right spot. And I'll show you a chart. That's a fair question to kind of have an idea. It's something really that should be part of our training to all employees so they don't discount it. So everybody knows somebody that's been shocked, and the electricians kind of play, I'd wire that live, I don't do lockout, tag out. They do it all day long. And yes, they know more about how to do it safely, but every one of them eventually gets bit.
Lots of times.
Yeah, lots of times. And when they stop working with 120 and they start working with 208, the bite is harder. And then when they go over to 483 phase,
they lock out.
They better lock out. Yeah, or we're going to have a real problem at that point. All right.
That'll walk your butt.
Yeah, it will. I'm going to kind of quickly go through this stuff to find the videos that we want us to watch, because we got some fun things I want us to do today too, and it's 4 o'clock, so I want to get some of the most boring stuff out of the way first so we can do the funner stuff, I think.
I did something bad one day when I was little. I turned on the microwave, but there was a toaster in it.
Toaster? What?
My mom used to store the toaster in the microwave, and I thought my food was there, so I started it. It was like, lightning is bad.
Yeah, that
Lesson learned.
that is quite interesting, and lucky. They say you can't put anything metal in a microwave, and that's not true. You can put metal in a microwave. It's going to get very hot. It may or may not cause additional shorts that take out the microwave itself. That's what can happen. And when that gets taken out and goes off, that can create a super bad scenario. We had a kid at the high school in Santa Clara, by Santa Clara there, that high school, a few years ago. They were modifying a microwave in a science project, and it blew up on him, and he almost died, and it burned his hair off and his side of his face, and he was in the hospital for about a year. I mean, it was a bad scenario, and his mom started kind of an awareness thing to say, hey, you can really get hurt bad on some of this stuff, and pay attention to what they're suggesting. Although you can still buy a microwave for $15 at the DI and do fun stuff with it. So just be.
Don't ever put grapes in the microwave.
Be very safe. Well, I don't know about that.
No?
There's a lot of fun stuff to put in
You ever
them.
started a fire?
Don't put a toaster in there though, right?
Yes, I lit a cup of coffee on fire because it was in a cardboard.
I put an aluminum. I should not be allowed to use microwaves. I put, you know, the tortillas have like the aluminum, like,
Foil on them.
yeah, to
Oh,
like
yeah.
close it. Well, I put it in the microwave and it was at work, which was worse.
Oh.
And someone was like, "There's a fire! There's a fire!" And I was like, "Please don't be me." It was me. Yeah, I caught on fire.
Now the worst part is your lunch is gone.
Yeah.
Oh, it's cooked quickly.
You're talking about the twist tie, right?
The twist tie.
Yeah.
It has like wire.
It's wire and it started the rest of it on fire, but it didn't ruin the microwave. You know. All right, we're going to look at, there's a couple of national bodies that control rules for electricity, and the National Fire Protection Agency is one, and they have a rule book that they publish, and there's the 2009 is still current. Oh, thank you. Seems like we ought to have sound.
Have you heard the news? NFPA 70E is changing the way electrical work is being performed across the country. Whether you own or operate a company, are involved in safety and compliance, or work with energized electrical conductors, these changes affect you. Just a few moments of your time now could save your company thousands of dollars in the future. Hi, my name is Vince May. Allow me to take a few moments of your time to explain the important information found in NFPA 70E, the consensus standard that OSHA has begun to use to enforce safe electrical work practices. The National Electrical Code is one of the oldest electrical standards and is sponsored by the National Fire Protection Association. During its formation, OSHA found the code to be a very useful document, but not exactly what they needed, as the National Electric Code is written to ensure safe electrical installations. In Article 90.1 of the National Electrical Code, we learn the purpose of this code is the practical safeguarding of persons and property from the hazards arising from the use of electricity. What are the three basic hazards of electricity? Probably the first to come to mind is shock or electrocution. Then there is the arc or fire. And finally, a blast or explosion. Which one of these hazards do you think causes the most deaths in industry? 90% of deaths are by electrocution. Which one of these do you think creates the most injury in industry? Over 75% of all injuries are from the arc flash and burning clothing. NFPA 70E, the standard for electrical safety in the workplace, details how employees should work on or near electrical equipment. The standard is divided into 4 parts, with Part 1 covering safety-related work practices, which is receiving the greatest attention due to the requirements for arc flash protection and the introduction of live work permit rules. Parts 2 and 3 deal with electrical maintenance requirements, or specific and unusual equipment, like lasers or battery rooms. And Part 4 is a direct reprint from applicable standards found in the National Electrical Code. NFPA 70E covers electrical installations for most buildings and structures, with notable exceptions for underground mines, airplanes, automobiles, and some electric utility installations. There are several steps in the safety sequence, and each plays a vital role in protection of workers from injury on the job. The first and best method is to eliminate the hazard, but that is difficult, especially for the electrician, who is far more exposed than most workers. Next is the use of engineering controls like lockout procedures, or the use of fast-acting current-limiting fuses. De-energizing and locking out an energy source is the best method for achieving an electrically safe work condition. Barriers and guards provide protection from inadvertent contact with exposed live terminals. Then there is training to educate the worker on how best to avoid the hazard. And finally, the last line of defense is PPE, personal protective equipment. Let's examine the hazard of shock. Using Ohm's law, we can see that an average person with wet skin will have a little more than 1/10 of an amp of current flow through their body at 120 volts. Even very small amounts of current flow can cause death. A hard-working employee generating a heavy sweat is at great risk for lethal levels of current flow.
That's one of the references we could look at. There's going to be a little bit of, disagreement about the milliamps because there's disagreement about where it goes in your body. But in general, what you're seeing there is it doesn't take much if it hits the right spot to wipe you out, to take you down. And 4 amps is all that's required for severe burns. And, your microwave oven is 15 amps usually.
In industrial environments, most of the exposed surfaces of a building are considered conductive paths. A GFCI is one of the best devices ever invented to prevent death by electrical shock. This next video illustrates just how quickly a simple electrical repair can become a tragedy.
I worked with Jerome for years. Mostly low voltage stuff. 480 volts, 600 volts fast. He never did wear his gloves, especially when he was troubleshooting. He felt that the gloves got in his way, kept him from getting a feel for what he was doing.
Well, nah, they get in the way.
I was helping him troubleshoot this circuit, and Jerome had to reach deep down into the bucket to test the output on a special relay that we had added to the control circuit. He had to use both of his hands to do it, so I was holding the meter for him. Well, he got the leads on the terminal block of the relay, but I got nothing on the meter. And it happened so fast, just like that. 1 second I was talking to him, and the next second he was being electrocuted. Well, I turned off the disconnect as quickly as I could, and I done CPR and everything.
Somebody, help!
He didn't make it. He just didn't make it.
Accidents like this one can happen to anyone who works on energized electrical equipment. Even the most competent and qualified electrician can make a fatal mistake. In a fundamental electrical circuit, current flows from the transformer to the main service, then through the circuit breakers and to the load on the ungrounded conductors or hot wires, and then returns to the transformer on the neutral or grounded conductor. Someone who's been shocked has become a part of that path. But even if a person doesn't become part of the path, they are at risk of an electric arc flash. If an ungrounded conductor or hot wire contacts the grounding conductor or grounded surface, we have just created a circuit with a very low resistance path. How much current do you think will flow from the transformer during this faulted condition?
All of it.
The answer I like to use is simply all of it. Whatever the transformer can provide. This is referred to as fault current. The circuit breaker refuses to sense the excess current flow or heat and opens the circuit. But for that brief moment, until the breaker opens, large amounts of current are flowing through the entire system.
I'm going to pause for 1 second there. We probably won't have time to talk about this much in class, but as we look at the risk of arc flash, this calculation of what is the fault current on a given electrical box is required by law to have been done. And in most cases, it's done by an outside agency to your company. And they must put that on a sticker on the cover of the electrical box. So when you look at electrical boxes in the workplace, they should say on that sticker what the maximum fault current is, or bolted current is a term they use. There are several different terms for that. But they do that based on exactly what machines are wired through that box. This is not a general, rule for, industry. And this is a calculation for that specific electrical box only. And it will be written on there, and then the calculation for what is the risk of an arc flash follows, and then the rules of how far you have to stay away from it if it's a big number. And if it's a big number, then you can't open the box. Somebody qualified has to open that box. I mean, open the cover to see if, just to open it up. And so there's a setback distance of 3 feet, 4 feet, 5 feet, depending on the risk of flash, and that's will be spelled out there too, and what kind of PPE you need to have if you are qualified to open it. You can't just do it, buck naked. You got to have the right PPE on when you do it. So I just paused it here because he's starting to talk about it. We'll look at that a little bit better later.
The result is an electric arc flash. The temperatures can reach 35,000 degrees Fahrenheit, and it does so almost instantly. This intense heat vaporizes metal, creating a bright flash and expelling molten metal, hot gases, and pressure waves. All of this in the blink of an eye.
All right, we've got a second part of this.
To understand this better, let's think for a moment about the worker who deals with electric arcs all the time. That's right, a welder. Welders regulate current flow to produce different sizes of electric arcs, depending on the amount of heat needed for the metal to be welded. This simple concept of a small amount of current will produce a small amount of heat, and a large amount of current will produce a large amount of heat, is necessary for understanding fault current. Now let's take another lesson from the pipe fitters and plumbers. Air lines, water lines, and gas lines all have to be rated to withstand the pressures of their system, or they would rupture or explode. Electrical systems have to be rated to withstand the large amounts of current flow created during a ground fault condition. The electrical withstand rating is called the amps interrupting capacity, or rating. It may also be called the short circuit rating, depending on the device or component being referred to in the electrical system. These numbers are usually in the thousands of amps category. When an engineer designs an electrical system, he calculates the fault current at each panel or disconnect to ensure that the components used are rated above the calculated values. Usually there are several standard levels or categories of short circuit ratings present in most buildings. Let's take a closer look at the drawing and some of the interrupting capacity ratings of the panels and switchgear. On the left side of this drawing, we see the main service, which is rated for 65,000 amps of fault current. There are several factors that determine the actual fault currents and withstand ratings, and so two seemingly similar panels can have completely different ratings. Like the two 200 amp 480 volt panels on the right. One has a 25,000 amp interrupting capacity rating, and the other a 42,000 amp interrupting capacity rating. It is not necessarily the size or voltage of a component that determines these values, as small wires and fuses can have large fault currents due to their location in the system. Now let's consider how long the arc is present. As I mentioned earlier, the circuit breaker or fuse will require some time to sense the overcurrent condition and open the circuit. If we use a 60 Hz system, there are 60 cycles or complete sine waves every second. 1/10 of a second equals 6 cycles. So when a fault occurs, some waveforms get through before the protective device opens the circuit. This number can range from as small as less than 1 cycle to more than 60 cycles, or a 1 second clearing time. In this next video from Square D, I want you to notice just how large the ball of fire gets in just 1 cycle of the sine wave, or 1/60th of a second.
Let's see what happens when the power is turned on. First, the real-time version. Now, a frame-by-frame replay of the same shot. In this case, the metal shorting link was blown away from the side of the enclosure, and all 3 phases became involved. Remember, all within 17 1/1000ths of a second.
Because of this danger, the 2002 National Electrical Code now requires arc flash labeling on all non-residential electrical equipment that is likely to require examination, adjustment, servicing, or maintenance while energized, to warn qualified workers of potential electric arc flash hazards. Let's take a moment and go over the 5 factors that determine how much injury a worker will suffer if exposed to an electric arc flash. First, there is the amount of fault current available in the system. Then there is the length of time the arc is present, and if it is in a box or enclosure that will direct the force. Finally, the distance from the arc and the type of clothing worn by the worker round out the list. This information is used to create the required warning label, so any qualified worker can select the proper personal protective apparel before working on the equipment. This tag lists the flash protection boundary, the level of PPE required for arc flash, and the approach distances based on voltage. NFPA 70E has created voltage tables to help determine electrical shock hazard distances for both qualified and unqualified workers from exposed, energized electrical parts. The three boundaries specified are called the limited, restricted, and prohibited approach boundaries. Specific requirements for clothing, tools, and procedures are necessary to perform tasks in each of these spherical boundaries. So a worker does not even have to be working on the energized component. Just coming near it with a tool or a body part will trigger the need for these protective measures. If a detailed hazard analysis has not been completed, or there are no labels on the equipment, there are tables found in NFPA 70E based on specific parameters that will help the worker select the proper personal protective equipment. All clothing, including undergarments, must be of natural fiber. Never wear clothing made from synthetic materials or blends with material like polyester or nylon unless it has been properly treated and tested. An ATPV rating, or arc thermal performance value, is used to determine the ability of a garment to withstand various arc flash intensities. There are 5 levels of hazard, numbered from 0 to 4, with 4 being the greatest or highest risk. Let's look at a series of tests on various types of clothing material that are subjected to arc flash levels that many employees face while performing their daily tasks. On the right, we see a regular cotton polyester dress shirt. On the left, a 100% cotton shirt. Now a cotton shirt on the left and an arc flash rated shirt on the right. This next video from ERI Safety emphasizes the need for proper arc flash protection.
I was working second shift and had to rack out a 480-volt circuit breaker as part of a preventive maintenance procedure. Now, according to the procedure, I was supposed to wear a switching jacket and hood, but since it was so hot and nobody was around to see, I decided not to wear the hood. I had it with me, I just didn't wear it. I had all the standard excuses. It was hot and uncomfortable, but I think the real reason was my attitude. It was a fairly new procedure, and I just didn't understand why I had to wear it, and I resented being made to do so. As I racked out the breaker, I knew something was wrong because I could hear an arcing noise coming from behind the breaker. I figured if I could rack it back in, it would be okay, but I guess I wasn't fast enough.
By not wearing the blast helmet, his head and neck were left unprotected.
I must have managed to close my eyes and look away right before it blew. That's the only reason I'm not blind. What's amazing to me is still, after my incident, there's still people that won't wear the jacket and hood. Listen, when the work is done, the hood can come off, but these scars, they never will.
The message is clear. Protect your employees and yourself. Don't wait for an accident to happen.
Hey, there's a couple things on arc flash that we've seen, and we're going to watch a couple more. And I think that arc flash is appropriate to talk about in this class because as OSHA looks at general electrical safety, we're going to talk about some of that during lockout tagout, but arc flash is something that most of us have had no training in and don't understand what it is. It's like, why is there something called arc flash? And I think maybe understanding a little bit about it would be helpful for us to know that if we've got a spot in our processes somewhere where there's potential for an arc flash, which, by the way, if you've got electricity, there's a spot where there's potential for arc flash, then we will have a better understanding on why we ought to have somebody assigned to learn about it, get the proper training in it, and share it with the rest of the team. Because what's going on, first of all, with electricity is an interesting phenomenon. Anytime we have two conductors, power at one, and a voltage potential across them, when they touch, there will be a spark. Always. Not sometimes, not depending on how much power there is. At teeny tiny bits of power, there will be a teeny tiny spark. And when those two conductors decouple, there will be another spark. So, when I turn that on switch, inside that switch, there is a spark. Every time. It's contained in the switch because it's a small spark, and we protect it. We have mercury silent switches, but it's not just because they're silent, because it's it doesn't click a piece of steel that's spring loaded. You hear the click on a switch. That's the two conductors springing together and then springing apart. And the click is designed to make it faster. So if you slowly do it, there'll be more of an arc than if you just do it really fast. So they try to trick it by doing it fast, but there's still a spark. And when you decouple it, there's still a spark. That's at normal wiring voltage, which is low amperage and low voltage compared to what industrial machines operate with. Even your air conditioner operates with higher current, and therefore there's a bigger spark. And most of the time, we put the switch over here, and this switch drives a low voltage, usually 24-volt wire, like your doorbell wires used to be before we had Ring doorbells. And that little wire triggers a starter switch to engage, but that's farther away from you. So that spark is safer by distance, right? Remove the hazard or move the hazard farther away. So that's what we do with industrial equipment all the time. So that spark exists. Now, because the spark exists under a normal switch closure, every time we close the switch, when it's abnormal, the spark goes a little bit different. It's shorting out on something. It's shorting to something. And it's maybe a longer spark. Maybe the duration of it is longer. Maybe the distance of it is longer. But what happens then is that spark now is heating up whatever's in the air around it. So if we smothered the air inside that switch with nitrogen, which is not conductive, and inert, no oxygen in it or anything like. It's more inert. It's not inert. More inert than the air we breathe. We have less chance of an arc. But if it's just the normal air around us, we get that air exposed to it. Well, what does the air have in it? 70%, 71% nitrogen, no problem. 19 or 20% oxygen, problem. 1% or less argon. That's what the air we breathe has in it. So oxygen, that's what we weld with, right? Oxygen and acetylene, right? So we got oxygen. What else do we have in the air? We have humidity. Not so much here in the Mojave Desert, but even yesterday, my little weather station said it was 44% humidity outside. That's high for St. George. 20% is more normal, even down to 10 or 12 or 14% is normal. But that also means that we have 10% moisture in the air, which means moisture is made up of what? Oxygen and hydrogen, H2O. So now we add a little bomb component to the thing, right? So we have water in the air around this switch that's shorting out. Now what happens is the oxygen feeds a fire. That arc flash is now catching on fire, and it's the oxygen that's catching on fire. The oxygen that's catching on fire is now burning the water, separating out the hydrogen and the oxygen. And as the hydrogen accumulates, we then get a secondary flash that blows the building apart. Because now that secondary flash, they say, is at about 35,000 degrees. And the wire in that box turns to liquid. And it splatters and sprays on the body that's standing in front of it, whoever that is. And if you've got protection, it splatters on that. It cools off fairly quickly. It heated up real quickly, cools off fairly quickly as well. So if you have a few moments of protection, you're probably going to live. You're probably okay. Even in the face of a really bad explosion, you're probably okay. Your body is going to get hit with non-liquid metal that might be like a bullet. It might do damage to you depending on how poorly you're protected, whatever that is. But that is what arc flash is about. And we're going to see a few arc flashes before we're done. I don't know if we'll see them today, but we'll see them. We are going to do some short circuits, though, where we have a little spark going on when we short something out, and we'll see what we're talking about. But just remember, one of the rules of electricity is anytime we get two conductors together, they will spark. And the more pressure that's on, meaning the more voltage that's on those two potentials, the farther the spark will jump. Okay? So you've seen a Jacob's ladder in science class where we've got two conductors that get further and further apart than a V, and we get an arc across them, and that arc goes up to the point where it no longer has enough voltage pressure to jump, but it jumps while it's down low. We play with that in science class, right? If I've got one at home, I ought to bring it in. We ought to play with it, I think. But we'll maybe save that for another class. Today we won't. What we're going to do today, take a break. Now we've had a little exposure to arc flash. We'll circle back to arc flash. We're going to do a couple experiments after we take a break. But when we come back from the break, I want you guys to figure out how we're going to do one experiment. So I'm going to. Maybe you can turn the lights on if you want to. Be careful for that spark. Good job.
I use gloves every time.
So we got an empty box that we can set up somewhere and shoot at if we want to. I want to test some safety glasses, and you guys figure how you want to test them. And I've got some safety glasses in here. What I was thinking is maybe we'll poke a hole, put the arms through it so it holds them up, and you can have multiple sides if you want, or no crossfire. We don't want to shoot it at the same time. But we have some sort of means. So we got some safety glasses here. We've got.
All we need is a volunteer.
Put them on.
Stand there. Take this. And I've got some just regular sunglasses.
Did you just buy those?
I just bought them. So if there's a pair that you really like, you can sneak them away before you shoot at them. I'm okay with that. So we want to shoot at some safety glasses that have the Z71 rating on the parts, and then we want to shoot at some sunglasses that probably don't. What I have to choose from is, you guys figure out, I think these all work. I have a couple of BB guns, and I have a couple of pellet guns in here. So I've got BBs, I've got some boxes of different kinds of pellets, even some hollow point pellets, and I've got some extra gas cylinders in there that I think are all new. They look like they are. And then there's a choice of guns in here. So there are some rules. These are not to play with, right? and we're not playing. We're doing a OSHA safety investigation here. So I'd like you to, if you don't know how the gun operates, either don't use it or ask somebody that does know. This is a pellet gun. It shoots one shot at a time. And this one, I think pumps up. One of them pumps up. This one pumps up. This one pumps, and it's a bolt action kind of a thing. some of these have the CO2 cartridges that come out of there. I assume that all of the cartridges are empty, but never assume that the gun is. And never, there's the same rules of a heavier firearm apply here. This one sounds like it's got BBs inside. Therefore, BBs will come out slower than the pellets, right? And it's less dangerous of sorts, but they'll all poke an eye out.
Oh yeah.
So the rules of handling a gun is they should never get inadvertently pointed at something that you don't intend to shoot. So be careful. Pointing at the ground is safe as long as you don't point it at your shooting. My son James will say, "Don't shoot yourself in the foot." That's not helpful. A quick Google for each of these makes and models will give you instructions on how they operate if you've kind of forgotten. I think we've all used stuff like this, but for some it may have been a long time. And so if there's a couple other things. If you are not comfortable around any kind of gun, I'm not forcing you to do anything around. Please keep yourself in a comfort level. We do want to shoot at sunglasses in the box. The box needs to be set up in a spot where there's a backstop of some sort, so if we miss the whole box, that we don't, take out the neighbor or, a window or anything like that. So we're going to go over by where there's some shipping containers behind the building B, where there's some safe area, I think, to set up a target. We will need to set up a firing line that nobody crosses with the target on the other side of that firing line, and we need one person that's in charge overall of gun safety in the firing line. So, because we're going to need to walk past the firing line to go see what we did, and some of you had training in that and would like to volunteer to do that. Anybody? You're in. Okay. Ivan's the gun safety officer for us, so don't fire until he tells you that it's clear to fire. Doesn't matter whether you think it's a problem or not. We have to be cleared by Ivan before you shoot. And when Ivan says, don't shoot, that means point to the ground and don't shoot. So with those kind of ground rules, I think we should be safe. So I've got an empty box, a box we can also shoot at. I've got a pocket knife, if you don't have one, that we can kind of cut into that. I'll just leave it here. I'd like that one back. I usually carry it with me, opening mail and whatnot. So while you go on break for 10 minutes, I'm going to go scout and make sure the truckers aren't turning around there tonight. I don't think they are. Make sure I have a safe spot out there. I'll go scout that out, and then I'll come back, and you guys can feel free to take these things apart, figure out how they work. I'd like us to do that while we're in air conditioning. Get it figured out here. And 1, 2, 3, 4, 5, 6 guns, or 6 of you. I don't know that all 6 shoot, but I think they do. They did last time we used them anyway. So you don't have to take one that's yours. You can share. I don't care how you do it. You guys take charge of that. Figure out what the experiment's going to be, of what we're going to be shooting at, what we're going to be learning when we do that. And I'll see you back from break in 10 minutes, and we'll start this project then at that point. Okay?
Hey, Steve.
Yes.
I have to leave
Okay. Do what you need. Just start this and then leave when you need to leave.
Okay, sorry. Otherwise, I would stay longer, but I'm just taking my nephew out for his birthday, so.
Awesome. That's the right thing to do.
Okay, thank you.
That's fine.
Take pictures of this, post it on my Snapchat. Ow! What are you throwing at me?
Shot fire.
What is this? Why do you waste marshmallows?
Yeah, I gotta put on my snap.
I gotta put the.
No.
You guys want to wear shades and be on my Snapchat?
The Arsenal.
The Arsenal. I'm already wearing shades. Let's see which one.
This one's BB.
So I'm guessing you volunteered to wear the glasses while wearing them.
You dry fired?
Well, I noticed he cocked them both. I shouldn't want anyone to
Yeah,
do it
yeah.
dangerously, right? Accidentally, like pointed
Okay.
something.
You're emptying them out, huh?
Yeah, I'm just like making sure the rest of yeah, that one had a teeny bit of air. See, they like.
He just said not to do that.
He's just
Well,
taking them out just
I'm
in case
making
it's-
sure that
yeah, there's
they
no-
literally 3 or 4 of those were just under
Under fire.
pressure. Yeah, so I didn't want anyone to accidentally shoot it towards someone else.
Like this one's got safety.
Including that one.
Hey,
So,
Okay, let's take a picture.
all these.
Yeah.
take a
like-
picture.
Let's take a
Every
picture.
one of those guns were.
That's crazy how like
No,
people
you get
risk to rob
one. You wear
places.
one. You guys wear one. I'm gonna take a picture of this. I'll wear these ones.
I'm watching here, Mr. Mazowski.
Yo, this is a strong one. I want to
Here
shoot
you
this
go.
guy.
You wanna wear those ones?
The red ones, the stunning shades.
Okay, everyone grab their
The
gun.
coolest shades are these. Oh, maybe that's
This one's mine.
This one.
Is anyone here got a gun?
I got one.
Boom.
They're like, who do these
Hey.
people think they are?
Point that in my face, dude. Crying out loud.
Alright.
I'm not in this.
Oh my gosh, why?
What?
Get some glasses
Get
on.
in here.
Here's the safety guy. You go to him.
Put the glasses on.
There you go.
This is not
Okay,
cool.
yeah, here we go.
Wait,
Whoa,
what's
whoa.
not even in here?
Okay, well, we'll take one with us for now.
Or it's down.
No, we're gonna take one with him. 1, 2. Yeah.
Now you gotta share it with all of us.
Oh, yeah.
They're gonna be like, what?
going on?
This
This is college?
I don't like this picture.
Like
What
first
kind
day
of
of
guys
school.
are
Now we
you?
wait for Melissa.
First day of school.
Is this not
Yeah.
What's that?
I should have
This
been
got
gone
to be
by
CO2,
now.
right?
Yeah, that means it's CO2.
I'm like doing everything. I have to go get the cake. I have to go get the present.
Some of these might be string loaded, actually.
This one's spring loaded, I'm pretty sure.
CO2.
Oh, I just
Did you just cock it?
Yeah.
Seriously?
with the
CO2.
That's heavy, man.
Spring loaded pump action.
Alright, this is spring loaded
Oh,
and
it's heavy.
Yeah.
and it's
Like an
loaded.
actual gun.
Dude,
like this
discharge it.
No, I locked it.
Yeah, just don't let like somebody pick it up and
Oh my
accidentally.
gosh,
Ooh,
his
this one's
BB has
nice.
sharp.
You're supposed to be the safety guy here.
That's why it's on lock.
Yeah, but first you
Safe.
cocked it.
It's safe. It's safe.
Watch, what if I didn't know any
No, it's
better?
locked.
I was just like, oh, hey, look at that, a button. Boom. Oh.
Keyboard.
Smells like
What?
it smells like the cardboard, or like it smells like a Sharpie when you write it with the Sharpie.
Um,
Order the cake right now.
It's a
Wait, you gotta pick up
vodka
the cake?
box?
Dude,
I
I'm
don't know.
doing everything.
It's just really strong.
I have to get a
It's
cake. I have to go shopping
Oh,
for
yeah,
a
it
gift in
smells-
like
it
30
smells
minutes.
Yeah, it smells like cardboard.
Oh, Melissa, do you want to take a picture of
No.
us?
Oh.
Yeah, with
She
us.
doesn't.
With the gun?
Yeah.
With a gun?
And your baby.
Hey, some,
You gotta put glasses right here. Okay, I call these ones. This one. I like those
What?
yellow ones. Those are cool.
You just took mine.
It doesn't say your name on it.
I did. I sketched it in there with the
I like
knife.
this guy.
Okay. You just wear. You just pick one of these. Oh, here you go.
I like this one.
Yeah.
Cop the,
I don't want those.
the teller.
Use
Fuck,
one.
give me the money.
Oh, these are cool.
We look so. You should have seen what we're doing. We look at kind of like
Wait, I
stupid.
had one
We're
in my
like.
hand. Is it? I think it's the one I
You wanna wear this one again? Here you
That
go.
might have something.
We can take
I
it.
Gotta do it again?
Pull my finger
Yeah,
on the
because we
trigger.
gotta have Melissa.
I didn't put my finger on the trigger.
Okay, you
tell
guys
me,
carry
just
the
because
guns.
Well,
Yeah.
CO2. This one's CO2.
Okay, want to
Give
picture?
me a button.
Yeah, no,
Yeah.
no, I'm taking a picture
Oh.
of all of us.
Just take it like a
That's why I was
selfie.
trying to give you the glasses.
Okay.
Again?
You ready to wear 'em?
Yeah.
Well, wearing
kinda.
like weird glasses too.
Wait, I like these
Okay. I'm gonna move my son.
glasses. Oh, wait, hold on. This matches my gun.
I've been once.
I've been
This
picked.
matches my
Hey,
gun.
is there
Belly?
6 guns? Oh, I was like, where?
Ándale, Pablo Escobar.
Okay.
ándale.
Ready? 1, 2, 3. Oh, wait, why do we look so serious?
Yeah, why are we
Smiling.
smiling?
I'm smiling.
It's like the first one, everyone's
Maybe
like,
why-
you should have just went like this, like in a line.
Yeah.
Oh, we're all wearing black, kind of.
Yeah, pretty much, except for,
Oh.
oh, you're still wearing black.
Sorry. Failed the assignment. The assignment. I failed.
Black top. Well, this isn't black either.
Should wear. Go get ski
Well, that
masks.
sounds fine.
Yeah, yeah.
I'm here to fight you when you.
I think there's a filter that can put ski
Cause I'm
masks
gonna order
on.
the
Huh?
cake right now.
On Snapchat it does that.
Huh?
There's a filter that puts ski masks on your face. That
Oh,
put-
Marley. Did Uncle Steve tell you what's gonna happen? Are you playing at me?
I'm not.
It's scary. Like I remember when I was little, I pointed a BB gun at a lady. She's drilled me. She's like, "Don't you get out?" It looked real like this.
Yeah.
Jeez.
Yeah.
Well, yeah, I mean, you should never point your
Yeah.
gun towards someone just
Yeah.
on principle.
Yeah. I didn't know that. I was
So,
like
yeah, it's-
10, 11, or 12, something like that. I didn't know that. I thought it was fun. Like, oh, look at-
Which ones do I want? The glass ones.
you want those to shatter, huh?
Oh, those are plastic. Are there some glass ones? Ivan, give me your glasses, man.
No, these are mine. Matches
Give me
my
those.
gun.
Dude, give me those right now.
No.
They're Gucci.
Give me those.
Nah.
Alright, fine.
I'll shoot at these.
I'll swap you. These ones are cooler.
No, look.
Way cooler.
Like brown?
So,
Oh, oh really? Is that? let me see.
Yeah.
Again.
You can
He's
see
like,
it. You can see
gold.
from a distance.
Closer.
He
My
wants those
eyesight
to
isn't
shatter.
good. I'm
You
nearsighted.
can have them later.
Alright.
I'm gonna shoot at
Yeah.
Okay, we'll shoot these ones then.
Take it back one
Or we-
second. You can see.
Wait, we gotta get these guns ready.
Dude, they're all ready. Stop cocking them in the classroom. You nut.
None of them are ready.
Dude. Oh, I see what you're saying. Loaded and stuff?
Yeah, we gotta get them
Well,
loaded.
these two, you load at the
No, yeah,
shot.
those are single shot.
Most of these.
What's this? How do you load this guy?
Actually, I want this to stay wide.
Oh, this is one shot? From the top?
Some of them might be single shot. I don't know. Good question. It's safety isn't probably.
Yeah, I have the safety on.
Oh no, that's a bunch. Okay.
Yeah, but where's the... How do you load? Oh, right through there.
That's like the air that helps it shoot.
This gotta be BB, right?
Yeah,
This
yeah.
gotta be a BB.
Sure, yeah.
There's two
There's
cartridges
no,
that cold air.
Pellet guns are generally single shot. Is there-
Alright, let's get this one loaded. Who's gonna shoot this guy?
I think
I'm gonna
Is
shoot
yours?
these two. Probably this one.
Where are the BBs at? Oh, I see. So look, you get some of these, and you put them in there. Yeah.
But do I have to pull something?
No. Yeah, you gotta pull this thing.
Oh, okay. Pull that in.
Yeah, point down the zone.
Oh.
That's your loading. Elder, which one are you shooting?
this one.
Yeah, get it loaded.
Load up the BBs.
Yeah. We got.
It's like universal. You can put it on both sides.
That's weird. Wait, is this a pellet gun?
Where'd they go?
Oh, sure is. Holy, what? That's cool.
You got a pellet gun, bro. Maybe. Maybe this guy.
Okay, what other glasses are we destroying? These ones are pretty ugly. These are the ones we're taking.
Alright, well, there's your loader.
These right here.
I think it's those. You want to load mine?
Yeah.
I want to shoot yours now. You got pellet handgun over here.
This is gangster right
Okay.
now. Is
What hurts more, pellets or BBs?
Pellets.
I've never been
oh,
shot by
nobody
any.
wants these ones, right?
Those are.
You want these ones?
Yeah.
I don't know if Tino wanted these.
What the hell is it? Oh, lost the.
Oh, there's so many.
Okay, so after it's loaded, what do you do?
Let me see. Here, do mine. Oh, you're dirty.
What's that?
This one's dirty. Oh, besides the CO2. You said they were all empty, right?
Yeah, I replaced all the seals. It's been obviously hanging around in this garage for years.
Are you using these?
Oh no! Oh no! We're gonna need a vacuum in here.
Can't vacuum, baby.
I got tired of standing.
Oh.
Oh, you did?
I don't know how to open the CO2.
Why is this bending though? Is this thing broken?
Oh, I think mine has some. Did you hear that?
Yeah.
Do you think it's full?
I don't know.
Some of them might still have some. Some of them pop kind of loud. So.
I heard it. I think mine's ready to go. Don't know if that's safety.
That helps so much. I ordered the cake online. Shoot Elder.
No. Not.
The mic.
Whose is this?
Mine.
I just want the heavy one.
No, that's yours.
This is not mine. Oh,
This is
this is yours?
mine.
You gotta load your BB. Come on.
Oh,
Where's
wait,
mine?
wait, wait.
Oh, he has a.
Oh, okay.
Looking at your CO2.
I'm trying to figure out how to get this canister
Those
out.
are like sharp. Like I've had a BB gun and the ones it's just this. Like that one's
That's a
like
pellet gun. I think.
oh a pellet.
Yeah.
Oh.
Oh, so.
I'm smart.
Oh, you got it?
Yeah,
Gosh.
I didn't know till they were guys were saying. Yes. CO2. It's gas. Gas, right?
Yep.
Cold air.
Oh.
Scared
That
ya?
scares me. Yeah.
Where's the trash? You have trash can?
You going to Tijuana tonight?
Oh, there you go.
I was gonna go, but my nephew's birthday's today.
Oh.
So
Okay, this one's ready. Is this one?
I'm the only
Melissa?
one celebrating
Yeah,
it.
thank
You want to do
Uh,
mine? I think mine has enough.
Which helps that I ordered the
Might as
cake.
well replace it, right?
That's good.
I wanted to go so
Yeah,
bad.
it's got.
Are you going, Melissa?
Oh.
No, we wanted to go yesterday, but it's too late. It's 8:30 my time. And
Okay,
Braxton
timing.
said it got done at like 11 something.
Yeah, so time because they do like intermission to.
Yeah, so it's too late for a work week.
I went in.
Okay. Oh, your lights on.
Camera.
Flash is on.
When you're trying to take a picture secretly.
He just shook it.
Guys, I'm feeling lightheaded.
All the CO2 just.
Yeah.
He's having fun.
There you go.
Here, no, I haven't left this room. Thanks, man.
Any more CO2
Are you
ones?
gonna
What am I putting in
load
there?
your thing or what? This is.
You just pick one for me or?
Oh, this is just standing here. Is this not yours?
Yeah, I'll take that. Let's-
Alright, load
Which one
it.
are you doing? Are you doing a BB too?
I'm doing
Everybody's
yeah.
gonna do besides Elder.
Yeah, I'm using
I didn't even know
pellets.
the pellets. So we opened the carton.
How do you?
The magazine.
Sounds like they're in there maybe.
We take them out from here.
Righto. No tape in here? What kind of classroom is it?
I like this one.
I'll
Put
probably
that
stay.
in this no, never mind. Don't use laptops.
Should we take a laptop out?
Yes.
It's been a long
Where's
time.
mine? Did you
Yeah.
What is
finish mine?
Para aprender los glasses, ¿sabes?
Oh, ¿ya lo está poniendo aquí?
Oh,
So cool that you guys all speak 2 languages. Sometimes I'm jealous.
Good learn one.
I actually may learn Spanish.
Oh, okay, that's cool.
Should we load this one? This is heavy. Is that
I need
loaded?
to learn.
No, not yet.
Yeah,
Oh, that's yours?
when I was in the UK, there's this lady who would like give me German words like a day, like to learn when I was there, and I was like, I can't remember
Mine's
all
ready.
of this.
Well,
Where's your?
They
I
call
know.
it Germany Deutschland.
You already put it in there?
Yeah, they don't call it Germany. That's like
Oh,
that's
yours
like
is
a
just a little bit,
foreigner
yeah.
thing, right?
That's awesome. I
Like
didn't
it's
know that.
called Deutschland. Deutschland. And she had a strong accent too.
I'm going to Netherlands.
That's so cool.
Safety's
planning
locked.
to go to Australia.
I don't know where safety
Don't
is.
mess
Oh, yeah?
with it.
And not Netherlands, no.
Don't worry.
Yeah, my cousin's wedding. Yeah.
Australia,
Australia.
quite beautiful. It's,
You been
it's
there?
harsh country. Well, I've only been to like Sydney and
Sydney.
there.
I'm going to Australia and then take a
Are you
ferry
really
to New
dropping
Zealand.
stuff?
Ooh, dude, New Zealand is where it's at.
Lord of the Rings. I'm just kidding.
Yeah, like go to the Shire. I'm not kidding.
Mhm.
Like the other thing I'd say do that's easily is worth it is luging.
Luging?
How do you take the...
Luging.
Is it here? Yeah, it is.
I
What's
think it's
luging?
not
Like to
not-
take the safety off. Take this one
Yeah.
off. See? It's just really
There's
hard.
luging is
have to pull
you
that
should look it
back.
up. Luging New Zealand, and what it is
Oh,
is
you mean like, I thought you said to go and do luging. I'm like, what's a luging?
yeah,
Oh, yeah.
oh yeah, you go luging.
Oh, you go, what do you
So
do?
it's basically Mario Kart.
Oh, okay.
It's
Yeah.
it's these big,
Oh.
massive,
Hard,
huge
huh?
green
That is
mountains,
kinda hard.
Yeah, I was like, what
and
the
it's
hell?
all
Usually it
downhill
just slides
tracks,
off.
and you're on
You're
a
not-
downhill cart.
Do you
Oh,
have
you're
it
going
put
down.
Yeah,
No,
it
I-
all relies
right
on
here, but I'm
downhill,
just
and
like,
you can like race
I didn't want
people. So freaking fun.
That
Done?
sounds like so much fun. Yeah.
So fun. I would go do that for a week.
Alright, take that
You
one
know
off.
it's, hmm?
Take it with you.
Can't take them with you.
You put a cartridge in it, didn't you?
You know
The-
what's scary? Like when I
No,
was in,
I didn't. Is that seal too?
in London, we did this thing they call
It's
punting.
open. Can't
And
be.
it's like, you go in the river and it's the, you know, kind of like Italy, those people who do it's
Yeah,
so hard. Like you would think that just like going on there is like so
Oh,
easy, but
it
it's
is.
like this huge stick
there's
from
no,
like
like,
this
pressure,
ground,
there's
like
no-
past this roof, and you
Alright.
just push off the
Give it to
dirt,
you.
The
the
boat?
mud. Yeah.
Yeah.
And like I almost fell in it like 4 times, like, and you don't go
Are these good
anywhere.
ones?
It's
Yeah.
hard.
Hey, what'd you do with the bad seal too?
Should we put this in or do we wait till we get outside?
All the-
I chucked them.
He whipped them.
Bless you.
Oh, that's just
Oh,
the
that's
locket.
the-
Yeah, that's the locket.
Quick release.
I just wanted to make sure. How do you know if it's safe?
Tino, ¿ya tienes su pistola?
As you pointed at me.
It's not even in there.
Están cargadas, ¿no?
No.
¿No?
No. I like that one.
¿Estas descargaron ustedes ya?
Yeah, those are ready to go.
Sí, como estas
I need to
están
get one
vacías,
of
le
those shades
metimos
for
las,
you. Peter.
Las balas.
Los bibis.
¿Cuántas
You guys, this might be derogatory, but what is Pluta?
Oh, God.
What is it?
He said,
Swear word.
Is it? What does it mean? Is it like
Like a
I'm
slug.
just kidding.
Oh, serious?
¿Cómo vas a hacer tú?
what the heck?
Esta.
¿Está cargada?
Sí, ya la cargamos.
There you go.
¿Están cargadas?
Ese es una por una.
So what is
Una por una.
hasta la
¿Dónde están
vista?
las? Están aquí.
A ver, sale.
Hasta la vista is like saying baby, like goodbye.
Tú vas
Well, I
a-
mean, hasta la vista, that's
Lo
from
puedes usar. Lo puedes usar también si quieres.
Terminator,
No,
huh?
ya lo cargaste.
No,
Yeah.
my
Hasta-
dad
I
used to have
want
a
to
shirt.
trade these.
Hasta la vista.
Oh, no.
Vista is like
Yeah,
view.
you guys got those in there good.
Maybe I'm
That one's out.
maybe I'm
Scary.
saying it wrong, but I always wondered what that meant.
Maybe it's loose, that's why.
You
not
know,
gonna-
we just learned about,
Safety.
yeah.
Dude,
Dude, look how wide you guys made this one.
Like this one's
taking
loud.
these out.
Sorry.
I want this one. Can you put that one?
They can smell it.
Why is
You
it
want
still
more?
leaking?
I don't
You
know.
wanna shoot this
It's
one?
just like,
No, I don't want to shoot
Oh,
this
you want?
one.
Yeah,
Well,
it's
no,
I
good.
want to wear this one. Oh,
You're trying to take hers.
I didn't know this
That's
was
so
like this.
rude.
Did you get water?
Doesn't this clear one look like it's for John Buck from Lilo and
Just put that one
It's
on
like,
the
look
top.
how wide they made
Well,
it.
I bent them. So they would. So that, I mean, because before they're like
Can
this.
we turn this way?
So
I'll say
it'll
the
shoot
leader.
or it'll ricochet. I wanted it to hit more straight on.
Oh,
Bent them.
I think this doesn't.
This is gonna crack. I already know.
No, it's
This-
fine.
See,
It's
it's
well.
not.
Well,
Well, like when you
this-
shoot it, it has a
but
kick
this
to
one's
it.
strong.
Yeah, it's a
I think
pellet
the pellet will
and
get-
seal too.
Or maybe not the BBs.
Yeah, see.
I think the pellet will get any
I
of
don't
them.
think Taylor
The
tightened it.
BBs will get
I'm
most.
gonna take an extra one just in case.
I didn't tie it very good, but that one's a stupid design. Yeah, it's just good. Well, let's do that side. It'll be a bunch of air.
See, it goes away. Yeah, I'm not gonna put it.
By the time we
outside,
start
I don't wanna
shooting,
shoot
I
it.
have to leave.
That sucks.
we should go now then.
I know.
Let's go then.
Yeah.
Maybe
we
he's
go.
out there waiting for us.
Yeah.
No, I said come back.
You said
Yeah,
it.
you said it's
But we can go look.
Yes, go.
Who just walked through the hospital?
Tino, did you want these?
Ah, yeah.
You want these ones?
Ooh, it's nice and cool.
I like these.
See, hey.
Lately, I've been buying glasses.
Have you?
No, like I just been going to dealers. They're
Really?
expensive.
Lately, I've been buying Star Wars merch.
Oh, okay, I don't mean to keep talking about the UK, but yo, they have like Star Wars stores. They're like the biggest fans.
Star Wars fans?
It's like I've never seen big fans of Star Wars fans until you get to London.
Seriously, dude,
I'm not
you're in
even
America.
joking. Like they have a Star Wars store, a Yoda store. Like
That's
people
awesome.
wearing Star Wars.
You know what would be fun though is to
I've
go
never
to
seen
like a Nintendo store.
A Nintendo store.
Yeah, that'd be sick.
You gonna put these in there?
Huh?
You gonna put these in there?
No, those are yours.
To shoot?
You want to shoot them?
Yeah.
I thought you wanted to keep them.
Oh no, I can't wear sunglasses because I
Because you have prescription.
Yeah.
Okay. I want to shoot these ones because they're ugly.
Okay, I'm gonna shoot them.
Oh, so you thought these were ugly? That's why you're saying I don't want these no more.
No, dude, you're rocking them. No worries.
I reckon these.
Ah, sí, Pablo Escobar, ya.
Yes, baby.
Yes, baby.
Whoa.
Oh yeah, I've been so hot.
He volunteered to wear glasses so he can shoot him.
Hey, that makes
You're
sense better.
so funny.
I'm hilarious.
You gotta send me the pictures.
Oh, sorry, I am. I was gonna send it through Teams.
That is way better.
So dumb.
I was trying to take one just for now, and I was like,
Hey.
"You're so rude. You're taking one without Melissa." I'm like, "I'm waiting for her to get here." But I'm taking
So
one right now.
when Misty and everybody wants you to present, you know, to do like after the course what we did, you show the picture.
The
Yeah,
picture.
I can show the picture.
Okay, that's
The
ready.
HR will be like, where you guys going?
Yeah. When they check our Teams messages.
Yeah.
The pictures, guys.
Hey, what's that? I take this one. See, put this one there.
Yeah. Okay.
Says you have given me
You want? Okay, so you prefer those ones?
a bun
Is that alright?
cake.
Let me see. Not too
Oh,
big.
that's
Maybe
okay.
this one's are better. You're
Dude,
right.
I just started to
Yeah,
like
this
it.
is better.
I told him I'm gonna be there around 5:45, 6 o'clock.
What time does the party start?
No,
She's the party.
I am.
She's the
I'm-
party. She's the
My
party
s-
maker.
My nephew's staying with us to go to school.
So you want to
His
use
mom
this,
lives
put it on
there.
top, or?
Ooh, that's an idea.
And
You can put it
like no
higher,
one's there to celebrate it.
Yeah,
so
you just put it like that.
he's always talking about like, oh, he
Oh,
never does
it's
anything.
way.
So I was like, okay, well, looks like we're gonna be doing.
There you go.
Wait.
That's awesome.
Oh, yeah. Did you get that one, Melissa?
I did, thank you.
You were good.
Alright, put that one.
Neat, I just smiling.
Put that one on the back, on the top.
Something like this.
Yeah, just to hold.
That will hold the glasses in, and it will prevent BBs from ricocheting after they go through.
If we get it in the right spot, though. If we get it in the right spot, they go.
Yeah, if we miss the box.
Is that good?
Those are mine.
We should,
They
you know,
should
for
those.
our presentation at Wilson, we should all wear these.
After we
You know-
shot holes through all of them, right?
No. We like at the end of our course, we have to go and talk about what we learned.
Do we really?
Yeah.
Yeah, I did
You
that
did
last
it?
time.
Joke.
No,
you
no,
did it?
no.
No, we
You'll
did.
literally be put on the spot. Like
Yeah.
you go up
For
there.
the leadership one you guys
All the
had to do?
leads are
Yes.
in there. Yeah.
Don't remind it. Don't remind
Oh.
them. Maybe it won't happen.
It was
Yeah,
Travis.
no one tell no one.
No,
But you have
oh, it's
your
when the
leadership.
whole course is done.
True.
Thing.
It's
I
not.
know,
It's
we
not.
went there.
Yeah, because they finished their course. Leo and them finished the 2-year course.
So we did it already.
So we
Not
did it
to
because we thought we were just gonna take that. But once we're finished with the whole course,
You have to do it again?
we go and talk to them. Yeah.
I just want to make sure you guys aren't wasting all your time.
Yeah.
What you learning, you can apply it. Yeah.
Yeah.
So I was like, we should wear these.
What you did when you changed your life and stuff.
I don't know. I was eating.
Yeah, Ivan.
Freaking Ivan.
Can I just look at the glasses for 1 second?
No.
If they're glass, we have to shoot them because they're the only glass ones.
Oh man.
Send me
Exactly.
that picture, Nelisa.
All right.
Oh,
if
yeah.
you like,
I'll
never
send
mind.
it to you.
I like these.
It's a waste. You're right.
Yeah, that's way.
Are you gonna take them?
Yeah.
Oh, we can take
He said you can. Yeah. Do you want a set?
My eyes
Oh,
are
really?
open
No,
and
I can't.
Oh yeah. Right.
Yeah.
Sorry.
The ones that you think.
Yeah, I messed them all up now because I wanted to stay in.
Oh,
Nelisa,
bounced right off the edge.
did you chew that?
That's a rapper.
I'm
It's a rapper.
I'll do it.
Pass it.
Okay. Steve.
This one?
I just like.
your cargo,
Steve?
short cargo.
You guys figure out how to shoot everything?
Yep, we're ready.
I
Okay.
said them too.
10 minutes away.
Oh, our
Yeah,
books
we're
are here.
Your books are here. That's
Hey!
how you go chase them
The
down.
minis!
Thank you.
Thank you.
I love the mini one.
Thank you.
Sweet.
Another green
Can't
one.
even get out.
Dude. Gosh.
Okay, so we've got some safety glasses. Everybody's gonna need to wear safety glasses. when
I was
you shoot.
wondering about that.
Ricochet does happen. Oh yeah, it can happen. I don't want it to happen, but I want everybody to be safe. So there's
I wear
safety
those on
glasses.
top of these because I can't see.
That's fine.
Yeah?
No, I don't take the glass glasses.
Okay, he's like.
And you're probably okay anyway. but-
Can I wear it over this one?
All right. So we are gonna go out behind the containers over there. It's a little bit of a walk, but we'll make the walk. We'll do this. We may not have time to do anything after we're done.
So we take all the stuff? Let's go?
Take what we need.
Oh.
Oh, you can take your stuff. We'll come back to it.
Oh, okay.
Yeah, it's good here. Thank you.
Sure,
I'm gonna get my cell phone and find that.
You guys want
Shoot him.
one more cartridge for that gun that was leaking?
We got it right here. There's one there.
You got an extra one? Okay.
Are you taking any?
No.
Oh, okay.
Yeah.
Well, they're all in here, right? Yeah.
Oh wow, you've got that's fancy. That's cool.
Thanks.
What things-
Made it myself.
Photographs of this.
Oh, my
Hey,
fuck.
what? Does anyone ever get their glasses?
Oh, no.
On the
I need
roof.
mine.
I got it.
Oh, it's cold.
Oh.
Good heavens, Ivan. Oh, I forgot about those. Oh, those are 14 probably.
Well, it was a success. The only person that got shot was a pregnant lady.
Yeah.
I got hit a couple times.
Oh, did you get hit
Yeah.
a couple times? Well, thanks for participating and nobody getting injured. We learned a couple things. These safety glasses are no good.
They're probably just a little older than the yellow ones or something.
They probably are. Oh man, they still have a Z rating on them, I think. Anyway, I'm good. Hope you guys have a great weekend, and we will learn about emergency exits and that kind of stuff on Monday. We've got some more electrical experiments that we didn't get done today that we will do on Monday. They're fun.
Sweet.
And, so that'll be good. Have a great weekend.
Okay.
You too.
Yep, thank you. See ya.
Going to play today, Steve?
Yeah.
Nice.
Good night.
Have fun.
Yeah, it's not hot out there, is it?
No. Not at all.
Yeah.
Oh, is that Annalisa's book? She forgot?
Looks like it.